there, welcome to another lesson in BED series, Biology's Explain This. I hope you enjoyed the last lesson, the introductory lesson on enzymes, and you attempted the question that you had there. So today, like we said towards the end of last lesson, we'll be discussing the models that explain the affinity between the enzyme and its substrate. How these models try to help us to understand enzymes being specific and what happens when the substrate molecules enters the active site. When molecules enter, what happens? So come along on this journey. Let's enjoy the biology discussion today together. Now, like we always did, let's look at our assessment objectives, our learning focus for today. One, at the end of this lesson, you should be able to state the models that describe the relationship between enzyme and the substrate and be able to describe the lock and key model of enzyme action and explain how the induced fit model differs from the lock and key model, explaining how enzymes and the substrate bind together and then how the reactions occur after they have become attached to each other in the active site. Let's begin to look at, let's start looking at the theories. Okay, you have the lock and key proposed by M.A. Fisher. That's, like I said in the previous lesson, 1894, that's the 19th century, towards the end. And then you have the induced fit model proposed by Daniel Koshland. That's in the 20th century. That is much more recent when you compare the two of them together. But let's dive in and get the details of each model. Now, in the lock and key, the enzyme's active site is seen as a lock, okay, whereas you have the substrate being the key. Of course, remember the lock at home. If you inserted the wrong key into the lock, it will not open. So that is the picture here. Now, the lock and key paints a picture of a rigid active site, which we are going to see something about it in the next model, how that model sees the lock and key. So this paints a picture of rigid active site where a particular substrate is the only one that can fit into it. So we have this lock and key telling us about the enzyme's active site being specific. So the idea behind lock and key concept is specificity. Again, let me say it with emphasis that the idea behind the lock and key concept is the issue of specificity that it talks about. So it tries to explain what makes an enzyme specific. In other words, no other substrate will form a perfect fit. But you see, there are certain inhibitors that can also enter the active site. They don't form a perfect fit, but they are still able to enter the active site. So we are going to be seeing the effect of such inhibitors called competitive inhibitors. They don't look exactly like you, but they are still able to cause a problem in the active site. So you can begin to look at the lock and key as a rigid site where only a particular kind of molecule could enter, as M.A. Fisher portrayed. And now the revelation that there are some molecules called competitive inhibitors that are daring enough, very bold and very daring. If they are around, they will enter the active site and compete with the substrate for the active site. And so let's look at the induced fit mechanism. Okay, now we said, if you look at this introduction, both of these mechanisms or models, they are discussing the binding of the enzyme with its substrates. Okay, but then the induced fit mechanism is like it has a slight opposition, a slight opposing view to that was stated by M.A. Fisher in the lock and key model, because unlike the lock and key model, it portrays the active site as something flexible, meaning it can be adjusted, that it can undergo a conformational change until the substrate is completely fitted into the enzyme's active site. I like the picture somebody painted about the stretch jeans that ladies wear. I mean, if you look at the way the world looks, those pair of jeans, they look very tight. But then the materials with which those pair of jeans, okay, that pair of jeans, but the material is stretchable. So as the lady is trying to squeeze her frame into that particular pair of jeans, the material is stretching. She's squeezing, she's moving left and right, and then eventually she succeeds in putting it on. Of course, there was a little bit of adjustment. The material with which the jeans was made, okay, was stretching. She was adjusting, moving this and that until eventually she fitted into it. That's one kind of illustration. Another one is if you sat on a foam, okay, bed or upholstery, whatever, you will see that the foam comes close to your buttocks and grabs the buttocks. So before you sat on that foam, it looks flattened. The moment you sat on it, there's a change in the shape where your buttocks occupy. There's a particular change. Okay, that place looks different from the rest of the foam. I'm just trying to let your mind's eye see, just to visualize the concept of an adjustable active site that can undergo changes, what we refer to as conformational change. So both the enzyme and the active, both the enzyme active site and the substrate are just likely to form a perfect fit, unlike the rigid active site portrayed by Amy Fisher in the lock and key model. And so, as we have said previously, once you have the substrate in the active site eventually, the R grooves in the active site come into act. Now, how do the active sites act? Okay, they can stretch the enzyme. So the stretching, they can stretch or bend it. You will see something like this in the next slide. When they stretch it, when they bend it, they make the bonds in the substrate very uncomfortable, leading to the breakage of the units that made up the substrate molecule. And those units, once they have become free, they can now recombine to form the product. So what you are saying is that in the active site, the R grooves make the bond in the substrate very, very weakened. They stress it because it's straining it, discomfort that eventually ends up breaking the bond. So the whole idea is to ensure that the active site is a location where bonds can be stressed or weakened so that catalysis can occur. And so look at this diagram. So look at the active site. The enzyme protein is in blue, okay? But look at it. The substrate is like that, flattened like a rod. But look at it. Both of them bent. Okay, when the substrate was entering, it was adjusted. You can see the dotted lines showing weaknesses there. And then the enzyme came closer to form a grip. Eventually, of course, the substrate was broken into pieces, and then the enzyme returned to its previous shape. So remember, we always say that enzymes are not used up in a reaction. Enzymes can, so the induced fit mechanism says that as an enzyme, I can be adjusted for you to fit into me. But then once the products are being released from my active site, I can go back to my previous shape. So we always say that enzymes are reusable. Enzymes are not consumed. They are not destroyed in the reaction in which they participated. They are just supposed to convert substrate to products, and they regain their shape and they can be reused over and over again. So as we round off this lesson, I hope you found it very interesting talking about the model. So when somebody is talking from now on, you can enlighten your friends and shed more light on the difference between the lock and key model and the induced fit. So let's look at these assessment questions. One, describe the lock and key model of enzyme action. Then describe the induced fit model. Number three, explain how the structural features of an enzyme allow the enzyme to carry out its function of catalysis, and focus on tertiary structure, that is the shape. Number two, still on how it functions, stabilizing bonds, the active site, substrate specificity, action, activation energy, and the rate of reaction. So you're explaining the structure of the enzyme. Let me put it this way: structure in relation to function. You can't function if you are not structured in a particular way. Or let's say you are structured to function in a particular way. So the enzyme has a structure. Okay, so you are discussing those things in context. Number four, explain the specificity of the catalytic action of amylase. Amylase just represents any enzyme. So explain the specificity of the catalytic action of an enzyme that is here exemplified by amylase enzyme. And lastly, for this lesson, is an enzyme's protein shape any different at the end of the chemical reaction it was involved in as compared to what it looked like before the reaction took place? Okay, what does this tell you about that enzyme, or let's say about enzymes generally? So please attempt those questions, send in your answers, and let's assess them and talk together. So lastly, as we round off, attempt the question like I said, send your answers to my WhatsApp number, my email address, Instagram, and to YouTube. I'll be glad to assess and get back to you, and then we work together towards your examination. Like I always said, nobody needs to struggle to pass an examination. We are at BEDS. We are here to ensure that you do very well in your examinations. Tag your friends, like and share our videos, pass them across, tell more people, tell that person to tell that person, so that can go viral and more people can do well in their examination. So if you enjoyed this lesson, I hope to see you in the next lesson as we continue still discussing the concept of enzymes. So thank you for listening. See you next time. Bye.